more properties and postulates. So far we've gone over some of the more basic ones. Now we're going to get more into like the geometric ones. So the first one we're going to go over is the segment addition postulate. First of all, we have a segment. So if we kind of go out to the side here to review, a segment is something that looks like this. There's also something that looks like this. Okay, so this is a segment. This is a line, and actually I'm not going to do that. So this is a segment. This is a line. And then this is a ray. Just a little bit of review. So a ray has an endpoint and an arrow. A line goes forever in both directions, and then a segment has two endpoints. So here we're talking about the segment addition postulate. So before we get to the proof, let's just go over the postulate. So let's say I have a segment. I'm going to put another dot right here. I'm going to call this A, B, C. When you're labeling a point, you typically use a capital letter. And what the segment addition postulate says that if you take segment AB, which can be noted with a horizontal line with no arrows on it, and you add it to segment BC, that is congruent or kind of equal to, okay, this part plus this part is equal to the whole thing. It's the length of the whole thing, which is AC. That is the segment addition postulate. You take the first piece plus the second piece, and it's equal then to the whole thing. Now, let's see how that plays out in an actual proof. So, two-column proof, just like before, work, reasons. And then number one, like I said, is always what you're given. Okay, what are we given? What are we starting with? Well, if I look up here, I am given that xy equals 42. Now, technically speaking, xy is a segment. This up here should probably have the segment marking, but we're going to forgive our teacher for making that error. Okay, now, we are given that xy equals 42. We're also given this picture. We're not going to write that in our proof, but this is part of our given, so we're allowed to use that. And we have to prove that n is equal to 5. So I'm going to look at this, and I'm going to look at my segment, and I'm going to go, oh, my teacher just introduced the segment addition postulate, so I might need to use that. So the first thing I'm going to say is I'm going to say, okay, well, I have a segment. And I know that if I take my segment, I've got xz, which is this first part. Okay, we can't use this yet because I'm just talking about the segment. So I have xz. If I add that to the other part, which is zy, then that should be congruent to the length of the whole thing, which is xy. Well, why am I allowed to say that the first piece plus the second piece is equal to the whole thing? I'm allowed to say that because of the segment addition postulate, which I'm going to abbreviate postulate there. Now, if I'm looking at that, I'm saying, okay, well, I know that this piece plus this piece equals the whole thing. I know that this piece is actually being represented by whatever these variables are, and ultimately I need to get to a variable, and I know that this piece is being represented by this. So step 3, let's say instead of xz, I know that xz is really 3 times n plus 4 plus zy, well, zy is really 3n. And then I'm going to do something here that I'll explain in just a minute, equals xy. Well, xy is the whole thing. Well, if I go back to my given, I know that xy is 42. What did I just do there? I went from all of these letters on my segment, which is my segment addition postulate, to all these variables. Well, that is substitution. I know that xz is represented by this, so I can substitute it in for xz. I know that 3n is being represented by zy, so I can just substitute it in. And I know that xy is 42, so I can substitute it in. Now, going from congruent to equals, this is something that I would not mark wrong, but just something to be aware of. When we're talking about segments, okay, these don't actually have physical measures. It's not like 15 or 12. So we use congruent because it's a geometric figure. When we switch over to variables, we also switch the sign to equals because now we're talking about numbers. Okay, numbers are equal to numbers. Geometric figures are congruent to other geometric figures. There's actually a step in the proof right here that's missing, where you, instead of saying xz, you say the measure of xz, but I'm not going to get that technical with you guys. And like I said, if you miss this, I'm not going to mark it wrong, but just be aware that's why we're doing it. Okay, now, step 4. We're trying to get down to n equals 5. I now have this algebraic statement. So the next thing I'm thinking is we can take this 3 and put it in there. So 3n plus 12, and then I'm going to keep this guy the same, so plus 3n equals 42. If you need to, come over here. 3 times n plus 4 plus 3n equals 42. We did that, so that's 3n plus 12. And why did we do that? That was the distributive property. Then I'm going to come over here. I'm going to put these together, which gets me 6n plus 12 equals 42. So step 5, 6n plus 12 equals 42. And then what did we do? We took the 3n plus the 3n. That is not addition because it's the addition property of equality, meaning it needs to take place on both sides of the equal sign. This did not. It was on one side of the equal sign. That is combine like terms. From here, I'm probably going to subtract 12. So 6n equals 30. So step 6, I have 6n equals 30. And that was subtract 12, and that was on both sides of the equal. So that is the subtraction property of equality. And then divide by 6. So n equals 5. So step 7. 5 is 5. That was division by 6. So division property of equality. Kind of screwed up there. Sorry about that. But division property of equality. And then always check to make sure you did what you were supposed to do. In a proof, they essentially tell you the answer right here. Okay? Unless your teacher screws up, which I will do from time to time. But prove that n equals 5. Well, there you go. N equals 5. That's exactly what it says. You're done with your proof.